Is it this one? So I'm changing. It seems that this now is live and clear. So it's loud and clear. Is it? Still not. At least when I'm looking this window here. So now it's good. Okay, now it's good. Yeah, we're a little late today, but the final thing is this one here. So I need to change the view. Simulation of a mechatronic machine, lecture number 3. Are you guys ready? Good. So what will happen today is mentioned here. So today we're going to look a little bit more about how is it we can define the constraint equations. And this is a very critical lecture because in a written exam and in a midterm exam there is always a question related to constraints. So please pay attention what I'm explaining you today. And then we're also going to discuss a little further about number of degrees of freedom. That's written in a green font because you already learned how is a number of degrees of freedom and how to compute the number of degrees of freedom. But today we're going to make a little bit of exercises, and my first in-class quiz will be related to numbers of degrees of freedom. So you may already log into Socrates when you will learn that there is a question related to number of degrees of freedom, but the system that you don't know yet. So you say that we still have a problem in the streaming? No. Okay.
I have a question regarding the tutorials. The last semester was the first mandatory for this course.
Okay, so there is a question regarding the guided tutorials. And the question was that are those guided tutorials mandatory?
Yes.
They are not mandatory. So if you wish to skip the guided tutorials, fine, that's fine. But we are organizing guided tutorials for you to help you to do your simulation assignment. Remember that this course there is 2 mandatory items that you must do. First one is a written exam, which you can actually do by making 2 midterm exams or 1 final full exam. Those are the alternatives. And then another one that is mandatory is a simulation assignment. And the simulation assignment will be something that will be based on your student ID number. And we will give you individual assignments that you have to complete by a certain time. And guided tutorials greatly help you to do that. Okay. So, but any other questions, comments regarding the practical matters or some technical stuff? So where the noise is actually coming from? From those 2 guys? So guys, what is your question? No question? Okay, can I have your attention then? All right, so you have a question. Yes, there was a misunderstanding concerning the tutorial on Wednesday. I got the message from John just a few minutes back, and let me see what the message actually is saying. So he mentioned that a group of students kindly asked me to repeat the tutorial on Wednesday. I mentioned that we could do that. So however, during that day we will have a review, also the second tutorial, just in case somebody asks. So this says that, so it will be organized. And there will be some further information via emails. Okay? Clear? Okay, anything else? Clear. All others are clear. Okay. So if things going to go smoothly today, there is a possibility that we can discuss about kinematic analysis today. So that means that we can solve the responses by using constraint equations only. And that's something that we already know what kind of systems we can analyze by using kinematic analysis. And those are the systems where the number of degrees of freedom is equal to 0. So it's meaning that we have equal number of equations than unknowns. So then it's all about solving the nonlinear, a set of nonlinear equations. And we have learned that from the previous courses, from the mathematics and other courses, how to do that. So we're simply repeating those tools to solve the kinematic analysis. A little bit unclear if we're really going to have a time to do that today, because there's so many other stuff that we have to cover before that. And one of the items we need prior to able to do the kinematic analysis is something called Jacobian matrix. It is related to numerics, and it is kind of like an important piece of information we need in order to solve those nonlinear set of equations. So that's what we're going to do today, and that's like the first very important step that I would like to do with you, to be able to solve the kinematic responses. And once we're able to do that, then we will start discussing about forces. And we want to express all the forces by using generalized coordinates. That's going to be our big objective in the rest of the course. Okay. So, short summary what we did last week. So last week we discussed about rotations in three-dimensional space. We used a method called Euler angles. And Euler angles is a method that based on 3 successive rotations. And we learned that the way it actually operates goes in such the way that the first rotation takes place around z-axis. So this is a first rotation. And then we have, original coordinate system and once rotated coordinate system. Second rotation will take place around once rotated x-axis. And then the final rotation will take place twice rotated z-axis. And what we can do then is that we can describe each one of these 3 rotations by using 3x3 rotation matrix. And those 3x3 rotation matrices are closely related to rotation matrices that we use in 2-dimensional space. Just to give you an example, here's our first 3x3 rotation matrix. And this submatrix here, which is 2x2 submatrix, this is exactly the one we are used to deal with in 2-dimensional cases. And then we have here the column that tells where the first rotation takes place. Similar way, so we have here the column that tells us where the second rotation takes place. And again, we have this 2x2 rotation matrix in a lower left corner of 3x3 matrix. In a final rotation, now the 2x2 rotation matrix is located in the upper right corner of the 3x3 matrix, and then the column tells where the rotation takes place. Clear? So then, successive rotations, mathematically, you can deal with them by multiplying matrices together. Once you do that, then that's how the final result look like. So that's how the 3x3 rotation matrix based on Euler angles look like. Let's practice. So I have here an example, and according to this example, I have a body that rotates 90 degrees. That's p divided by 2 around the vector that is unit vector, and the unit vector has a component according to this equation here. So there's a component, hold on. So there's a component in a x-axis, a y-axis component is 0, z-axis component is 0. So that means that the rotation takes place around x-axis. All right? So now we simply, where we're going to define this 3x3 rotation matrix is that we have to give a values to these 3 rotational coordinates or rotational angles. So what's going to be the first angle, which tells how much the system is rotated around the z-axis? 0. because the system is not rotating around that axis. That have to be 0. All right? Makes sense? Second rotation, if referring back to this, hold on, this slide here, the second rotation takes place around x-axis. So how much is just second rotation? That's going to be exactly the one that the system rotates. So it's going to be p divided by 2. All right? The final rotation, that again have to be equal to 0. So these are our angles. And then we simply substituting these angles to this monster here, which is a 3x3 rotation matrix based on Euler angles. Once you do the math, this is how the final result look like. And based on this one, you can tell that, okay, the first column tells that the rotation takes place around x-axis, and then this is actually something that resembles the case in planar rotations. Makes sense? So it's all about substitutions. I don't know if you have a time to look at the next weekly homework, but the next weekly homework, I'm asking you to introduce the rotation in such the way that the vector v is not this one here, but is one where the first component is 0, second one is 1, and the third component is 0. So that's what that means. It means that the rotation takes place around y-axis. Okay, y-axis. So let's go back to this slide here. Y-axis. Well, we don't have a y-axis. So what that means? Is this like no can do? Or is there any way that we can make this happen? There's a way we can make this happen. Because you can take this gyro here, and you can put the gyro any orientation in a space you want. So similar way, we can introduce this rotation. But we need a little bit of help from all of these 3 parameters. So we have to use the parameters to kind of switch the place of rotation angles. And once we do that, then we can solve the problem. How it's going to go? It's going to go in such the way that, hold on. Oh, I still need to go back here. So, because maybe the best way to explain it is to show it here, these figures. Now what we want to do here is that we want to introduce the rotation around this axis here, this y-axis. But that's a parameter that is missing. So how is that we can make this happen? Well, we can make this happen in such the way that we will introduce the rotation around the z-axis in such the way that the x and y-axis will change the place. They will go and change the place, and then I am able to do my rotation. And then my final rotation, I will compensate the first rotation by making that minus in a sign. I need to repeat this again. So let's go this picture. Let's go this figure here, or this slide here. So first I will introduce this rotation. By the way, what was the name of this symbol again? Phi. Phi. Okay. So I'm going to introduce the phi in such the way that my x and y-axis will change the place. All right. So I have here, my coordinate system is x, y, z. This is my coordinate system. So I'm going to introduce the first rotation in such the way that x and y will change the place. How much is that? 90 degrees. So it's p divided by 2. All right? So then I have the x-axis that is pointing the direction of y-axis. Then I do my rotation, whatever is amount of that. That's it. And then I will compensate my rotation by putting this axis back to original configuration. So it's a p divided by 2 minus p divided by 2. That's how it goes. All right. Yes, sir.
How about if you have more like complex vector, for example, 1 to 1?
1 to 1.
Yeah.
1 to 1. 1 to 1. So you're asking like 1 to 1.
Yeah, for example, or it could be 1, 1, 1.
Okay, so 1, 1, 1. Okay, so first of all, you have to make this, hold on, 1, 1, 1. So that's what you're asking.
Yeah.
Okay, so the first rotation, that's going to be clear because it's a, this one is here. let me explain it this way. So you can make this in such a way that you can rotate each one of these axes one at a time. And then you can multiply these matrices by using this successive rotation principle. So that's how it goes. So you can get started by something that you first have this vector here. Then you do the rotation. You will get result. That is a rotation matrix 3 by 3. You do the same for the middle one. You get the 3 by 3 rotation matrix. And then the final one. And then by using this multiplication, you can get the final orientation. So that's the way it goes. Good question, by the way. Awesome question. Okay. Have you guys noticed that when you log into YouTube side of this course, there's a picture of me by like this? You know where this is coming from? It's coming from these coordinates in three-dimensional space. You always have a coordinate system with you. And now I know that there's a different schools, different people, prefer left and right hand coordinate system, but I prefer left hand coordinate system. In the left hand coordinate system, the good thing is that the right hand tells you what's the positive direction. So these fingers tells you what's the positive direction of the rotations. So that's how it goes. And because we have to consider the rotations all the time, I would like to propose that this is going to be our gang sign. Next time you see me in a corridor, you don't say, "Hello, Aki," but you say, "Respect." Respect. And even better, this. All right? So you're in my gang? Okay, good. So that's how it goes. All right, so you know how to solve the next weekly homework? Yes, sir.
Are the Euler angles always set exact, or can there also be another combination for the?
So the question is that is the Euler angles always with this a little bit inconvenient sequence, xz, or is there something else available? There is something else available. So if by referring the material from last week, these are the different combinations. So you can pick the one you like the most if you're building the software by yourself. But most commonly one used is this sequence, the one we're learning here. That's the most commonly one used. Why? I think that's because I'm not sure really, but it's just if you look at the Adam software, it operates in that principle and many others too. So it's often used. But answering your question, there are other sequences available too. Okay, so then, so that was an example. Then what else we did last week? So we looked how was velocity, and the velocity is the one that consists of two components. So there's a translational velocity, and there is an angular velocity. An angular velocity is something that there is two other components that are needed. This one here is original rotation matrix that is rotated 90 degrees positive direction. And we got that by differentiating the rotation matrix with respect to angle theta. All right. Then this one here is a vector U-bar that tells what is a particle we're looking at. And then in case of acceleration, we have translational acceleration. Then we have an acceleration that is quadratically related to angular velocities. And then we have the velocity that is linearly related to angular accelerations. So those are the three components. This one here is a translational acceleration. This one here is a normal acceleration. And then this one here is a tangential acceleration. So those are the three components. And then the last week we also learned how to compare the number of degrees of freedom. This is very mechanical. So absolutely no shortcut, absolutely no thinking when you do that. You're just following this certain procedure over and over again. The procedure that I'm expecting you to follow is shown here. So you just first compute the number of generalized coordinates. And that will be depending on the number of bodies. So in two-dimensional case, the equation that tells how many generalized coordinates you need is going to be this one here. So this is going to be the number of bodies multiplied by 3. So if you have 10 bodies, you have to have 30 generalized coordinates. Now this one here tells what are the number of constraint equations. And that really depends on what kind of constraints you're dealing with. I have some examples that shows in planar cases and three-dimensional cases what's the number of constraint equations you need. But I need to get back to that a little later today. Just a few more minutes and I will get back to this. Okay, so we have 3 possible scenarios regarding the number or degrees of freedom. So we can have over-constrained system, meaning that the system cannot move. An example is this one here. So I have, if I first compute the number of generalized coordinates, I have here 1, 2, 3 moving bodies. So it's going to be 9 generalized coordinates. All right? So 9 generalized coordinates in this system. Then I have here 1, 2, 3, 4 revolute joint. So it's going to be 2 multiplied by 4. And then I have here sliding joint here, translational joint. So it's going to be plus 2. So it means that this is going to be 8. So this is a total of 10. So it's minus 1 degrees of freedom. System cannot move. All right? This one here is kinematically driven. So originally I have 1 degree of freedom in my system, and then I'm going and constraining the final degrees of freedom. And the way that I'm constraining that, it will be based on the predefined motion. So I'm telling the crankshaft that you are no longer free to move as you want, but instead you have to follow the certain pattern. The pattern is mentioned here. You have to follow this, and that's considered as a driven constraint. So it's driven the system, and that's another constraint. So it's meaning that I have 3 generalized coordinates, 3 constraint equations. So with help of constraint equations, I can solve the response of my system. That's all that I need to know. Then the final scenario is something that I have this 1 degree of freedom, and that 1 degree of freedom is actuated by a force or a moment. And it could be anywhere in the system you want. There could be multiple forces. There could be one moment here. There could be a single point here. You just have to compute. You have to create the equation of motion in order to solve the responses. Go ahead, sir.
Can you go through this equation, the calculation which you did?
This one.
Yeah.
Can I repeat that?
Yeah.
Okay. So the way you can calculate the number of degrees of freedom, you have to know the number of generalized coordinates. And the number of generalized coordinates is always depending on the number of bodies. In 2-dimensional space, it's going to be 3 multiplied by number of bodies. That's the equation you can use. And then this one here, which is a constraint, that really depends on your case. That's how it goes. We will practice. There's going to be a slide that I will help you to kind of understand the concept. And right after that slide, there's a question where I'm expecting you to compute the number of degrees of freedom. Any other comments? Clear? Okay. All right, then last week you pointed out that there was a missing symbol. No. Why? It's not yet time to go home. Oh God, now this is going to take a little while to put it back on because the system is a little slow. So first this guy is cooling down and then he's warming up again. So, okay, tell you, let's do such the way that, please stand up. Let's stretch a little bit. Like, is it feeling already that this makes sense now? This all makes sense? Oh, it's a Monday, so it's a little hard. It's a little hard. I don't know. I guess it's still going to take a little while to put it back on. Is this overheating too, or why it is behaving this way? Okay. How is the streaming? Streaming is still all right.
Yeah.
Still all right.
See the slides.
What was that?
You still see the slides.
Yeah. So here you go. So the best way to learn is YouTube. The live is no good. Live is no good. Okay. Is it back on? Okay. Look at that. Now it's warming up. Is it the streaming still all right? No effect to streaming. 5 seconds and then we back. 2 seconds. And we back. All right, so can I have your attention, please? So you pointed out that there was a missing symbol in the last week, and yes, there is a missing parcel operation here. So please add that to your notes. All right? Because this is a parcel rotation matrix parcel theta. That's how it's supposed to read. So the parcel operation was missing there. Okay, constraint equation continues. So here are the different choices for two-dimensional space, and this really tells you what are the number of constraint equations you need in different cases. So the first case I have here is a fixed joint, which, by the way, is not a good idea to model, because typically this, it makes no sense to model a body that is unable to move. It's a crown body, and if you model, say, the structure that is like this one, and you attach this to crown by fixed joint, and these together by fixed joint, it's still a crown body. And you're just losing the generalized coordinates for nothing. So it's not a good idea to use it. But for sake of generality, I still have it in my list. So if you have fixed joint, you need 3 constraint equations to describe it, because then the body cannot move. So you have to eliminate the rotations in the rotation and translation to 2 different directions. So that's a total of 3 generalized coordinate, 3 constraint equations, Then the revolute joint. Revolute joint, what we already learned, and the revolute joint needs 2 constraint equations to be modeled. So 2 constraint equations are needed. Translational joint, that will be also 2 constraint equations that are needed. What are the equations? I will explain that to you a little later today. And then the primitive joint. And the primitive joint, by the way, is a special case. It's something that, there's a, point here that belongs to this beam-like body. And the point has to stay within this slot, or within the predefined curve. So that 1 degree is a 1 constraint equation that is needed to model that. So it means that, if there is a slot, this beam can go up, it can rotate, but it cannot travel to this direction. So that direction only is constrained. So that's a primitive joint. So it's kind of like a slot where the point can slide back and forth, up and down this time. All right? Makes sense. Okay, let's compute. What's the number of degrees of freedom? So I have here 2 different kind of mechanisms. So let's calculate those together. And next slide, I'm asking you to compute it by yourself. So you ready? Okay, so let's practice. So how many how many generalized coordinates I need for this system here? Okay, so how many I need? How many moving bodies I have? Okay, 1, 2, 3. All right? So it's going to be how many generalized coordinates? 3? 9. Oh, yes, 9, not 3. 9. Okay. How many revolute joints I have? So it's 1, 2, 3, 4. What? 3.
4, but not a 0.
How much? 4. 3. Somebody saying 3. 3. You think 3? Yeah, this is not really revolute joint. It's just a point, you know, to kind of like it's like a joke a little bit. Yeah, it's not really a good joke, but you know, this is, you know, to try to entertain myself. And this is what we're doing in the written exams too. So we're providing something that we hope you to get confused. Okay, so this is not the revolute joint because it's not coupling any body. So it's just a point in the body. All right, so I have 3 revolute joint. So it's going to be 3 multiplied by 2. And then how many sliding joints I have? Translational joints. 1. So it's 2. So what's this? That's 8. So 1 degrees of freedom. The system can move one way only. Yes, sir. This one is a translational joint. Okay, this one, I have 3 revolute joints. Each revolute joint needs 2 constraint equations. Okay? What about here? What's the number of generalized coordinates?
6.
Okay, so I need to tell that this is a hydraulic cylinder. So this is like one body. Here's another body. So this is a cylinder and a piston. So here's the same thing, cylinder and a piston. So how many bodies we have? 4, 12 coordinates, correct. So both are correct. So 12. All right. How many revolute joints? I have here 1, 2. What? Counted? This is a counted. Yes, it is counted because it combines the bodies. So it's 3 multiplied by 2. So that's 6. Then how many translational joints? 2. Okay, so it's going to be 2 multiplied by 2. That's 4. So it's 2 degrees of freedom. So they can go down together like that, and then they can move like this. So those are the 2 ways it can move. You got it? Clear? Okay, what about this? What's the number of degrees of freedom? Okay, so I need to explain. So I have here certain number of bodies, and then the primitive joint. Would you like to go and check this? Squeezes. Oh yeah. Oh no. Look this direction. I don't know how to stop. So are you able to enter your answer? Is it on? Okay, so I need to check that from my phone. So why is so it's kind of weird that it's So would I like to stop the current activities? Don't know. I don't know. Squeezes. Yeah, I have no idea what's going on here. So reports results. Oh yeah, I see that now. So we have 73 students in this time, and Now it seems that out of the 73 students, 39 entered an answer already. So what about you guys? Did you already enter your answer? Okay. 40, now it's going to be 44, 45. So soon we're done. Okay, is this too simple? So let me see, 55 students. Gonna wait and say 10 seconds, and then I'm gonna close this one because I wanna show that how to compute the correct answer. 61 students already entered the answer. How is gonna be success rate? 99%, 100%. 90%. 75. Yeah, 75 is a threshold. So if it is less than a 75, we're going to go back to the beginning of today's lecture. I'm going to repeat everything that I mentioned today. If it is more than that, then we will continue. Okay, so now I have 65. It seems that you guys already done. Okay. 67. And now I'm going to close it. The thing is that you cannot see the answer, but I will tell you, and I will be honest. Look at that. So it's 87%. 87%. Okay, 6% say that is 2 degrees of freedom. 1% is saying that is 3 degrees of freedom. So the correct answer is 1 degree of freedom. Where that is coming from? So we have 2 moving bodies. How many generalized coordinates? 6. 6 generalized coordinates. Then I have some number of revolute joints. How many? 2. Then I have 1 primitive joint. What's that? 1. That's 5. 1. System can move one way only. All right? Clear? Okay, so then another in-class quiz will be coming soon, but not yet right now. Okay, so this is a little bit of boring part, but let's shortly summarize this. So different constraints have different names. You know that in a midterm exam, you can carry all the material you want with you, including Google. So you can have a Google and lecture material, my recordings, everything you want. So that tells that most probably I'm not going to ask anything like this because it will be very easy for you to check from the lecture note. So if I'm asking like, what's the non-holonomic constraint? So it makes no sense. But just for your information, holonomic constraint, it is something that most often we're dealing with. So they are defined as an algebraic equation in terms of generalized coordinates. So they depending on generalized coordinates only. A revolute joint is an example about holonomic constraint. Non-holonomic constraint is something that involves inequalities or generalized velocities. When there is a constraint that tells how to roll without slipping, when the disk is rolling in a surface without slipping, that's the constraint you can define by using non-holonomic constraint. If you want to make a bicycle model, you need to deal with the non-holonomic constraints. Then there is a Holonomic constraints that are kinematic constraints. So they are like just, again, revolute joint. And then there's a Holonomic constraints, driven constraints. Those are the ones that introduce the motions to system. Again, if I have, let me make a drawing here. So if I have a box here, the box is in a surface. And if you introduce the motion, if you say that this coordinate have to move according to certain mathematical function, that's going to be called as a Holonomic constraint because it's a driven constraint. So it's introducing the motion to system. So it's like active constraint. Other ones are passive constraints. Okay? Just for your information. All right, what about in 3-dimensional space? You know, in a 3-dimensional space, if you're using Atom software, these are the screen captures from Atom software. This is a matrix that tells how many coordinates are eliminated when you're using different kind of joints. Let me give you an example. So if you're using a fixed joint, one showing here, then you will eliminate 3 rotational degrees of freedom and 3 translational degrees of freedom. So it's meaning that you need a total of 6 constraint equations. All right? If you're using a translational joint, you will eliminate 3 rotational degrees of freedom and 2 translational degrees of freedom. 5 constraint equations are needed. And the similar way, you can check other kind of like basic joints from this matrix. And then you can also build the joint by yourself. And the way you can make it happen is that you can use a joint primitives. Joint primitives are considered as a piece of joints. You can combine them as you want. And this matrix tells certain possible scenarios how you can combine them. Conventional joints, these ones, you cannot combine. But primitive joints you can combine in a different ways. All right? All right, so then let's look at something that is a little bit of mystery to me. And this, right after this, we will have a break. This is now in 3-dimensional space. So I'm using these matrices that are available here. I wanted to calculate what's the number of degrees of freedom of a door. Door that can be open or closed. Okay, so what is that we have in a door? So we have, a door, like this is a typical scenario of the door. So I have here door, how many generalized coordinates I need in 3-dimensional space? 6. Okay, then I have here, if you look at the door here, how many revolute joints we have? We don't know, but I guess there's 2. Yeah. 2. Okay, so I have here 1 revolute joint, another revolute joint. Okay, so let's go to this slide here. So let's compute if I have revolute joint, the revolute joint is here. So I need 5 constraint equations to describe 1 revolute joint. And now I have 2. So I need what it is. 10 constraint equations. 6 minus 2 multiplied by 5, that's 10.
No.
Yes. That's it. So we cannot leave from this room anymore. So we have to stay here rest of our life. Mathematically proof. So would you like to give a call to your parents or girlfriend? What's wrong in my proof? Minus 4 degrees of freedom. Remember, minus degrees of freedom, what's that? That's a system that cannot move. Cannot move. So here it is. Any explanations?
I think because they love the same coordinates, so they are different coordinates that they lock.
They're locking the same coordinates. So they are not independent constraints. Oh, you kind of like, because I was expecting to make a story like 20 minutes out of this, call the 911 and, this kind of stuff. And now you just say that, my proof is incorrect. So no need to call, by the way, it's a 112 that we should call. So no need to call anywhere because we can still leave from the room. Why? Because, the constraints have to be independent constraints. And these constraints are not independent. They are eliminating the same coordinates. And if, this next slide is direct copy from the lecture notes. I don't know if you guys read it. Obviously you did. So it's mentioned here that the constraints have to be independent. So they cannot be dependent on each other. Now when you have 2 similar constraints eliminating exactly same coordinates, they are dependent on each other. So that's not the way to go. So the way you should deal with them is just to use the independent constraints. I know this is sometimes a little bit of problem because particularly in a 3-dimensional space, you can end up to have a little too many constraints because you're easily eliminating the same constraints. And this is a particular problem in a three-dimensional space. So you easily have something that is redundant system. And redundant system meaning that you have constraint equations that are not independent, but they are depending on each other. And that's not the good modeling policy. So you should try to avoid it, because if you have redundant system, then the reaction forces are unclear. So, and you can make a wrong interpretation concerning reaction forces. Okay, I know that you want to go and have a break soon, but I have 4-bar mechanism in three-dimensional space. So let's compute the number of degrees of freedom. Very common mechanism, and I have revolute joints that combines the different bodies together. So let's look. So first of all, what's the number of generalized coordinates? 18, because of 1, 2, 3 moving bodies, 3 multiplied by 6, 18, correct. So it's 18 generalized coordinates, and then I have certain number of revolute joints. Each revolute joint needs 6 constraint equations. So how many revolute joints I have in a system? I have here 1, 2, 3, 4, right? So it's 5 multiplied by 4, what's that? 20. So it's minus 2. That's because it's a redundant system. It still can move. So if you make a model like this, say commercial software like Adams can understand that you are not an experienced user, and it can eliminate automatically some of the constraints. And it only gives us, tiny sign, okay, I noticed that you made a redundant constraints, and I decided to eliminate some of them. Which ones? That you have to be really careful to know which ones are eliminated. So the better way to model this is to take one revolute joint off and use like inline primitive. Then you will have 1 degrees of freedom. Inline primitive. Yes, sir. Okay. Whole story from the first slide. This one. This redundant business. Okay. This system is redundant because I'm eliminating the same coordinates overly many times, or too many times. I should only eliminate the coordinates once. And here I'm eliminating them too much. And that's why I end up to have a degrees of freedom that is minus 2. It's supposed to be 1. It's supposed to be 1 because if we make a model of 4-bar mechanism in 2-dimensional space, in 2-dimensional space, this is a different story. I have how many moving bodies? 3. So it's 9 generalized coordinates. How many revolute joints? 4. 1. So it's 1 degrees of freedom. So what's the problem in 3D? In 3D, the problem is that if this is how the 4-bar mechanism is moving, I'm constraining this motion, this perpendicular motion, too much. It would be enough to use inline primitive joint here. It will be enough. You got it? Okay. Inline. Okay, let's go back and check the inline primitive joint. Here, inline primitive, here. So it's 2 constraints. So let's go back and compute it again. So I have 18 generalized coordinates. Then I have here 1, 2, 3 revolute joints. So it's 5 multiplied by 3, that's 15. And then plus 2, 17, 1 degrees of freedom. You got it? Okay. Break. 10 minutes.